So we're going to talk for the rest of class today about a brand new distribution. So far we've talked about normal distributions, which are Z procedures. We've talked about T distributions, which are very similar in shape to normal. Just as kind of a reminder real quick. Do we remember? So normal distributions look like this. This is our Z's, right? What does the shape of a T distribution look like? Fatter tail. Similar shape though, right? Still unimodal, still symmetric, but it has like fatter tails, like these tails, like if we're going to talk about, like these are become like really close, right? So like fatter tails at the end, right? T distributions, but still the same shape. The new distribution that we're going to talk about is something called a chi-squared distribution. It is not unimodal and symmetric. It is skewed right. It is a skewed right distribution. And we will always be looking at probabilities in the right tail. Okay, that's just something interesting to know. There will not be a two-tailed test here. It will just be looking at probabilities in the right tail in terms of the shape of the distribution. On the back of your formula sheets, I do believe there are chi-squared tables. Oh, no, I didn't print them. On the back of your formula sheets, I just had the normal distributions. I do believe that the AP will give you a chi-squared table. I have just really completely gone away from tables altogether, but you can look in the book. It tells you how to use them if you're interested. I just think the calculator is so much better. So just like we did normal CDF, T CDF, you can imagine that there's chi-squared CDF as well, and that's what we'll be using to find our p-values in this distribution. So what we're going to be able to do here is do a brand new hypothesis test. There are three, count them, three chi-squared tests. And so we're going to look at just one of them today called the goodness of fit test. And you'll notice in the problems that I gave you, the front is goodness of fit, and if you turn it over on the back, it's the other two tests. And they're called homogeneity and independence. Okay? And so homogeneity and independence are together for a reason, and we'll talk more about that on Friday. But goodness of fit is kind of on its own little thing. Still uses the same statistic, but the way that it's calculated is a little bit different in terms of the lists and that kind of thing. Chi-squared does deal with categorical variables. Remind me what categorical variables are, because we've been doing so much with means. We just took a quiz on means, right? And means are numerical or quantitative, right? So what is categorical? Give me an example of a categorical variable. Colors, great. And we'll actually look at some of the colors today. Colors, I don't know, things you don't put numbers to, right? There are counts, however, much like there are for proportions, right? It's like the number, the proportion of people that have green hair. I don't know, I'm making something up, but that kind of idea where you can still have counts and proportions. We're just going to not write them as a fraction with chi-squared. We're going to be looking at just counts total, just when we count in each category. We're going to be looking at categories in terms of our objective here. Okay? So we're going to be not doing all of this today because we don't have enough time to do all of it. But like I said, there are three tests. Today we are going to be looking at the chi-square goodness of fit test. A lot of times it's abbreviated this way for obvious reasons. Okay? And so we're going to spend some time looking at just that today and what that looks like. There are others, like I said, on the back of your sheet. I've highlighted them. There's the one for homogeneity. It's not homogeneity, it's homogeneity. Think about homogenize. It's a kind of like milk thing. And then you have your independence. Notice this also has the word association with it. So on the back, if you want to, where it says independence, you might want to put association as another word that will kind of clue you in as to you're going to use this test, okay? So independence, association mean the same thing. Is that okay? All right, we'll talk about that more on Friday. But let's look at some differences. Now, when we think about our hypothesis test, what, in terms of the state, plan, do, conclude, stepwise, let's talk about the plan for a minute. What was the plan for all the other tests we've done so far? What are we looking at? The conditions, and how many were there? Guess how many there are for this one? One. Uno. Kind of nice, right? The only condition you need to check here well, there are two. You have to say that thinking about a random sample, okay? So we should have randomization. So there really are two, sorry. But this is the other. The condition that we're going to be checking is that expected counts, and we'll talk about what that looks like in a minute, all need to be at least 5. Basically, that's telling us I have a large enough sample size, okay? And that 10% condition and the normal condition all lead to that whole, is my sample size large enough? So same kind of idea, there's a different way of going about and looking at it, okay? Again, when we're looking at chi-squared, we're talking about counts. How many in each category, okay? Now, something that chi-squared has that's similar to t is they have something called the degree of freedom. Degree of freedom is actually going to be called, well, to find it, is the number of categories minus 1, okay? So the degree of freedom for a chi-squared is categories minus 1, at least for goodness of fit. Now, when we get to Friday, it's a little bit different for the other tests. For goodness of fit, it's categories minus 1. Not counts minus 1. That's important, okay? Categories. So think about colors. However many total colors we're looking at, to add those up and just minus 1, okay? So that's going to be our degree of freedom. But people get confused with counts, so just be careful. So it is just the categories, the general groups, number of groups. All right, so let's look at an example. Want to? So let's look at the example that I've given you. And it talks about, go ahead and read the problem to yourself. It talks about trick cereal, again with colors, which is exciting. So I'm glad Kevin brought that up. Colors, flavors, whatever. So read the example to yourself for just a second, and then we'll talk about what we need to do to solve. Okay, so we kind of understand the question really here. So we're trying to add, the question being asked is, are the colors in trick cereal uniformly distributed? Now, when we talk about writing a null and alternative hypotheses, they've already kind of written them out here for us, okay? Before we get to that, though, can someone explain why this is a chi-squared test? What is the clue to us that that's what we should be doing here? Okay, so I have some counts in several categories. Would you actually? There's only one category. It's color. Would you agree? There's one variable, I should say. There's one variable, several categories in that variable. All right. Why couldn't I do a proportion test, like a 1 proportion z test here, or comparing 2 proportions? How many proportions do I have? 5. I can't do 2, right? I can't compare 2. I've got more than 2. If I was going to do, I could translate these to proportions by putting them over the totals, couldn't I? And I could find the proportion of tricks as grape or lemon or lime or whatever. But because I have multiple proportions, that's your clue that it's a chi-squared test. Okay? All right, good. So let's look at the state. So we know in our state we have to name the test. Why is it chi-squared goodness of fit? Well, because I have one variable, and that variable is color. Now, there are 2 things that I can look at. I can look at something called a uniform distribution. I don't know why I'm having trouble saying that. Uniformly distributed, which is what I'm going to do here. I can also be given a distribution to compare it to. And so on Friday, we're going to lead with an example that looks at M&Ms, okay, and their color. The idea is that, well, it used to be, they've changed it since, but several years ago, M&M Mars Company told us the proportion of blue, red, yellow, brown, whatever the colors are, orange, M&Ms are in a bag. And so they would say like 13%, 14%, 18%, whatever, of each color. So you had a distribution of color, and you would take your sample and compare it to that distribution. That's one thing you can do, okay? And we'll do that on Friday. But today we're going to look at just uniform distribution. What does that mean to you? What do we expect to happen if it's uniform?
All
They should all be the same. Do you agree with that? If the colors are uniformly distributed, we expect all the colors to be the same. We expect. I'm using the words for a reason. Look at what we have in our bag. What do we have in our bag is what we observe. So this is going to be what we call the observation, the numbers that are given to us. And we're going to have to calculate what we expect to happen. Okay? So how can I find what we expect to happen if we expect them all to be the same? Find the total, however many of these are. Find the total of them. And then there are, you said 5 categories, right? So the total divided by 5. So take a second, add them up. What is the total divided by 5? Sure. So we should have gotten a total of 2,615. Okay, and when you divide by 5, we expect 523 to be in each flavor. Would you agree? Okay. Since it says the word uniform, that's what we're going to do. If it gave us the percentages of each, we would find the percentage of the total and find those counts. Are we okay with that? Expected counts, by the way, can be decimals. Because that's what they can be. Observed cannot. Interesting fact. All right? But these aren't, so it works out well. Looking at the null and alternative hypothesis, once we find our expected and our observed, which is going to be important for us in our calculation here, when we talk about our state, we have to have the name of the test. We've decided on what it is. And we have the null hypothesis, and it's always written in words, by the way. There is no symbols that we'll use for chi-squared. But the null hypothesis is that the flavors are uniformly distributed, and the alternative is that they are not uniformly distributed. Okay? It's just simple as that. When in a chi-squared test of goodness of fit, the null hypothesis is always either uniformly distributed or it matches what was given to us. It's one or the other. Our sample distribution matches what they claim it to be, the percentages all match, or it's uniform. And then the alternative is always, nope, they lied. Okay, always, which is kind of nice. I like to say always. It doesn't happen very often. Our plan. There are 2 conditions. What's the first? Random. Does it say in here that it was a random sample? No, we're going to assume it, okay? We'll have to assume that our sample was collected randomly. Randomly. Thank you. And then what was the other condition that I said was brand new? Expected cell counts are greater than 5. Well, look at them. They're all 523. Would you agree? So we can say for sure. And you wrote them down. You've told me what they are. That's important. All expected cell counts are greater than 5. And essentially that just tells us that the sample is large enough. So we're good to continue. Okay? What was the next step in our hypothesis testing? Do. Okay? And in our do, we have what's called a test statistic and a p-value, right? And this is the new part. On your formula sheet, on the very, very bottom right-hand side, it tells you in words how to find the chi-squared test statistic. And it says that it is the observed minus the expected quantity squared divided by the expected, except for it has a big summation formula, some sign in the beginning of it, doesn't it? So I'm going to just kind of write that in there. That just means sum, means we're going to add them up. So what does that look like to us? Well, you're going to take each cell and you're going to use those numbers. So our observed for grape would be 530. minus 523 quantity squared divided by 523 plus, are we okay with what I'm doing? Let's keep going. Then it would be 470 minus 523 quantity squared divided by 523 plus, do you understand the pattern? Okay, good. So I'll just continue to write it here. What did I leave off? 420? By looking at my observations and comparing them to, well, do they look uniform to you? It doesn't really look uniform to me. So I'm just, making a wild guess that I'm probably thinking that they're not uniform. All right. I'm going to you want to just trust me what these numbers end up being? Okay, good. I was hoping you'd say that. All right, so we have that. Each of those, and I'm just going to write these down because I'm going to show you why they're important on the calculator. So there should be 5 of these. Look at these numbers that I'm writing down. Are we okay with what they correspond to? So this corresponds to the first one, right? This one's going to correspond to this one, and so forth, okay? Good. Look at the numbers and tell me what you notice about them. Why are some larger than others? What'd you say, sweetie? I'm sorry. Yeah. The bigger number you see here means that it's further away from the expected count, right? That kind of makes sense because you're subtracting the expected from the observed and dividing by. I mean, think about the calculation you're doing. It kind of makes sense. But you get a test statistic here, okay? And it's not like if it's greater than 3, it's unusual or less. It has nothing to do with 3 because it's not a symmetric distribution anymore, right? So we can't really tell right now what's unusual and what's not unusual. I will tell you the larger your chi-squared value is, the more unusual it is, okay? Which kind of makes sense. So when we think about a p-value, remember it's a right-tailed distribution. So we're looking at 47.572. So we're going to be doing a chi-squared CDF. Going to use your test statistic. Helps if I don't leave numbers out. Out to the right. And then what do you think I'm going to have to put in there? What did I have to put in with t's? Degree of freedom. What's our degree of freedom here? 4, the number of colors, number of cell counts, right, minus 1. So we have 5 colors, therefore our degree of freedom is 4. Go ahead and tell me what the p-value should be. I'm curious as to what you think about it. If the P is low, reject the hoe. Are we rejecting the hoe here? Yeah. That might be the smallest p-value I've ever seen. Would you agree with that? Okay. So we have, I can't count, was it 8 zeros? Okay. Did you get that? Something really small, right? So the P is low. We're going to reject the hoe. So for time's sake, let's just say the p-value is less than 0.05, which is our alpha, right? What are we going to do? Reject the null. Therefore, we can say what in context? The color distribution of trick cereal is not uniform. Well, we have evidence to suggest that anyway. We can't say for 100% sure, right? So we have evidence to suggest that the color distribution is not uniform. How do you feel about it? I happen to think sometimes they're a little bit easier. Your calculator does do this for you. I would like to show you that on the calculator, but we'll probably need to do that next class, okay? So we'll start with this on Friday.